Alright, so welcome back to particle physics and the Standard Model. This is lecture 18 and last time we got our first taste for quantum field theory, right. So we saw how to write down a consistent theory, putting both space and time on an equal footing because we need to satisfy relativity, and then we saw how to also quantize such a theory. We concluded by saying that we need equations of motion such as the Klein-Gordon equation, right. Remember we wrote a shorthand form for the Klein-Gordon equation this way, acting on something which we inferred to be not the wave function, but on something which turned out to be a field because we set this function to be a function of space and time, right. So we demoted space from an operator, position from an operator down to a label, and we kept time as just a label, correct. And then we call this object a quantum field. Agreed? Field because it is a function of position and time, and quantum comes from the fact that it is an operator. And then we asked, if it is an operator, then what is it operating on, and we said it operates on the Fock space, and that way creates and annihilates particles. There is a vacuum in the Fock space, the ground state of the Fock space, from where you can start producing or creating particles, and this is what we mean by excitations of the quantum field. Okay, excitations meaning you create these bundles of energy and momentum that we call particle states. Good? Okay. So this might sound a little esoteric to you now, the whole procedure of taking and making a quantum mechanical equation relativistic, and then suddenly demoting position, and then calling these quantum operators and so on. So this might sound a little abstract and esoteric. So I am going to start by motivating why this kind of a step is necessary and why this seems to work so well. Okay, why does quantum field theory work so well in describing the real world that we live in? Okay. So to do that, let me spotlight certain features of the natural world that you may not have thought of before. Okay, certain not very obvious things but very startling things nevertheless. Okay, so here are a few observations that only quantum field theory seems to address. All right. For instance, okay, so I am going to list 3 or 4 of these observations of the natural world. The fact that the world is made up of several species of indistinguishable particles. Okay, what do I mean by this? If I take a piece of chalk, right, from a box, and then I take another piece of chalk from that box, for all practical purposes they look exactly the same, correct, 2 new pieces of chalk. But are they really completely indistinguishable? Not really, right. If you started looking in a microscope, or even if you started inspecting these things closely, you will find very minute differences between them, right. And in a microscope you are definitely going to find differences in how the calcium carbonate molecules are arranged and so on, correct. Or take 2 new iPads from a shelf. For all intents and purposes they look the same, but again there are sure to be differences, minute differences between them, correct. So this is true for every object, every macroscopic or even mesoscopic object in the universe. No 2 stars are the same, no 2 planets are the same, right. No 2 objects really are exactly the same in every possible way, right. but there is one class of objects that does have exactly identical, everything is exactly identical between any two specimens of the species, and that is fundamental particles. Do you agree? Take any two electrons in the universe, they both are exactly the same, they both have exactly a mass of 0.511 MeV, they both have a spin of half, right? They may have different momenta and energy, but that comes from initial conditions. I can always arrange them to be, I can always go to a frame where they have the same energy and momentum, correct? They have the same charge and so on. Anything that you want to characterize them with, they are exactly the same, right? So fundamental particles are the only really indistinguishable objects that we know in the universe, and that is a very startling fact, right? Where do you get such indistinguishable things? When we talk about Pauli's exclusion principle, hypothetically we talk about two indistinguishable states that are under exchange, but even in real life we do have these exact copies, correct? And such a fact that for every species, for the photon, electron, muon, W boson, whatever, there is tremendous numbers of these exact identical objects all over the universe that can only be explained using quantum field theory, okay? And how can you explain that? Because in quantum field theory, as we just said, the field, which is an operator, right, acts on some Fock space. It's like a Hilbert space, except you can also create and annihilate particles in any number here. Let us say it acts on the vacuum, okay, and in particular there is a creation operator sitting in the field. That is what gives rise to an electron state, for instance. So I can have a single electron field permeating the universe, all right, and that single electron field acting on this abstract Fock space will give rise to all these exactly identical electrons all over the universe. That is the way we understand these indistinguishable particles, okay. Okay, let us look at another startling fact. Once again, this is something we encountered before. It is the spin statistics relation, right? The word statistics is a bit confusing here, because what is really the statistics? Well, it comes down to exchange between particles. So I like to call this a spinterchange theorem. That is how I remember what this is, okay. I just made up this word. This is a relation between the spin of states and what happens to these states under interchange of two of identical specimens, right. So what is this again? We saw this a few lectures ago, right. We saw that all half integer states, half integer spin states, are fermions, that is antisymmetric under exchange, correct? That is what we define as fermions, right, using Pauli's exclusion. And all integer states are bosons. So there is an exact mapping, right, which are symmetric under exchange, okay. So again, if we had not discovered quantum field theory, we would have still discovered this observationally. We would have seen that all the bosons, like photons, which you can make lasers out of, that means the bosons are symmetric under exchange, correct? You can form coherent states. The states that you can use to make these coherent states, like laser, turn out to have integer spin, and then all the matter particles which you cannot exchange, right, until you pick up, unless you pick up a minus sign in the wave function, they all seem to have half integer spins. So this fact is something that you could not have explained if not for quantum field theory. Remember, even in our cartoon proof of spin statistics theorem, I had to use a fact of quantum field theory, right. Okay, good. So here's another startling fact. This is so startling that we don't even really think about, we don't even notice it. This is the fact that the world contains not only particles but also their antiparticles, right? A priori, there is no reason that all the particle states should also have a counterpart where all the charges are flipped, where the charge conjugate states have to exist. Correct? So, again, the only way we can understand the existence of antiparticles is through quantum field theory. A quantum field is necessarily expanded in terms of creation and annihilation operators. We will see this very soon. And that is how you give rise to the notion of antiparticles. Okay? Okay. So those three, I think, are seriously the most startling things that quantum field theory, in just one shot, by just defining the concept of quantum field, you explain away all these things in a very minimal and elegant way, right? Indistinguishable particles, the spin statistics theorem that there is an exact matching between spin and interchange, and the fact that there are antiparticles for every state that we know of. Okay? So those three, if you don't remember anything else, if you remember those three, that's good enough to motivate quantum field theory. Okay? But there are more things also. Alright? So I'm going to start naming them with Roman letters to show that, to me at least, they are not as important as the first three. Okay? But nevertheless, they are there. And these are also pretty startling if you think about them. For instance, we keep seeing the phenomenon that particle processes involve the absolute creation and destruction of particle states. Again, this is a notion that we are somewhat used to, but it's pretty startling actually. Okay? Take for example a very simple process, beta decay, which we've been seeing again and again, right? So what has happened here? Just like that, the neutron, which is a state pretty well defined, right, all of a sudden has utterly disappeared, and out of nowhere I've got a proton and an electron and an antineutrino, correct? These are three completely different states. The neutron is is characterized by completely different properties. One has suddenly disappeared and the other three have appeared. We've been using this all along the course, but we never paused to think about how odd such a fact is, right? We are used to two balls, a football and a tennis ball, crashing into each other. Imagine the football suddenly disappeared and then turned into a baseball. The tennis ball suddenly disappeared and turned into, say, a shuttlecock or something, right? That's what we are seeing all over the place. This is a notion that incidentally bothered Richard Feynman's father a lot. Where did the electron go in this process? Where does the photon appear from? So these were the things that he really could not understand, and Feynman didn't have a satisfactory answer to give his father. Okay? So it's very hard to explain this to a layman, to a lay person, but once you accept quantum field theory as a good description of the world, it becomes the most obvious thing. Okay? In the language of quantum field theory, with operators annihilating and creating processes, especially when you understand what Fock space is, which is where these things happen, it becomes the most natural thing. Okay? And here's one more. The fact that forces are associated with particle exchange. This is not a direct observation, this is an inference, okay, but an inference that seems to work really well, right? So again, this might, you might have heard this since high school or something, right? Forces, the electromagnetic force is mediated by the photon, the weak force is mediated by the W bosons and Z bosons, you exchange these particles and so on. But it's not really that intuitive actually. Why should forces correspond to some exchange of a particle between two states that experience this force, right? What does this really mean, right? So for instance, Maxwell's equations, right? Maxwell noticed that even when you didn't have any sources, you had self-propagating waves of the electric and magnetic field, correct? This is after all what light is, right? So they seem to have a life of their own, the electric and magnetic fields, even without sources, right? So that might make you think that, you know, on some sense these fields, even if there are no particles to feel the force, the fields themselves are fundamental in their own right, correct? And this was proven, this intuition was proven to be right when we discovered quantum mechanics, and then these fields, their excitations were inferred to be the photon, and the photon could be thought of as a particle, correct? And the exchange of the photons is what we infer as electromagnetism between charged states. Agreed? So see, just like that, starting from fields, we understand that forces come from mediation or mediation through particles, mediation by particles, right? And similarly, Yukawa predicted the existence of a pion, right, using the same notion, because he proposed that the pion is the particle exchanged in the strong force, correct? Force carrier of the strong force between neutrons, or I'll just say nucleons, neutrons and protons, right? And indeed we did find the pion this way. So Yukawa even predicted what the mass of the pion had to be, about 100 MeV, and we went there and found the pion this way, right? So this inference also turns out to be correct, and once again you might make all the inferences you want, but if you want a more fundamental theory for where this comes from, that is once again quantum field theory, okay? And I'll make one final observation and move on to other things. Another very interesting fact about nature is that the coupling constants that we know about, right? So what is one coupling constant that we already know from high school? Newton's constant, right, of universal gravitation. We also have the coupling constant from electromagnetism. There are many ways to write this. One way to write it is the fine structure constant, correct? These coupling constants characterize the strength of forces, correct? Forces, interactions and so on. Now I'm going to turn around history a little bit, okay? I'm going to turn around the order in which these things happened, and I'm going to say that even if quantum field theory had not been discovered, we would have seen that these coupling constants are actually a function of the energy scale at which we measure these processes, okay? In other words, these couplings, the technical term for this is run, actually run with the energy scale. So if I measure the fine structure constant, what is the value of the fine structure constant? The usual answer people give is it's 1 over 137. For some reason this number got very famous, right? But that is only at an energy scale, you know, of let's call it the electron mass, okay, atomic scale basically. Suppose I built a bigger collider which acts as a microscope for me, okay, and I were to measure this at much higher masses, let us say 100 GeV, much higher energies, right, which is the electroweak scale or the weak scale or the Fermi scale, there are many names for this. You would find that this number is actually 1 over 128, not 1 over 137. Okay, and then if you were to build an even bigger collider, which we don't have now, and then you measured it at 10 power 5 GeV or something, it will be even bigger than this. Okay. So even more startlingly, even the electron mass, which we think is 0.511 MeV, if you were to measure it at a much higher energy scale, the electron mass is also different. So all the free parameters of the standard model are actually not constant across energy scale at least. And by energy scale, we also mean distance scale, right? Because by Heisenberg's uncertainty principle, energy is inversely proportional to distance scale. So higher energy scales means I resolve it into smaller and smaller distance scales, right? And this observation, so this observation came after the formulation of quantum field theory, but I am going to just assert that imagine that you had already made this observation. The only way you can explain this is again only through quantum field theory using, I will just write the name, we will catch up with it later, using concepts of renormalization, okay, and a related concept which is the renormalization group. Again a byproduct of field theory in general, but particularly quantum field theory. It is thinking about quantum field theory that Kenneth Wilson came up with these ideas. Okay. So I thought this was important to explicitly state why we really do want to go on this ride of quantum field theory. The rest of this course is going to deal with quantum field theory. Okay. So I think it is important for you to know why we take up this language seriously and why it seems to work again and again. So there are all these broad features about the natural world that are only answerable in the language of quantum field theory using quantum operators that are actually fields, namely functions of position and time. Okay. Now for all the merits of quantum field theory, there is one consequence that that is still very problematic. Okay. So I just told you, I just talked up quantum field theory for you, all the great things about it, but as soon as I start thinking about this language, there is one immediate logical consequence. Okay. Let me just write what it is. It is called the cosmological constant problem. Is an immediate consequence of thinking about quantum field theory in this way, which if you ask me is the biggest problem in physics right now. Okay, it is the mother of all crises. We have no idea what to do about this. We have a few ideas, but none of them are satisfactory, and we are going to catch up with this very soon. Okay, right in the very next lecture. So I am going to build up to this. Okay, we will see what exactly the problem is, and this kind of calls into question a lot of the postulates of quantum field theory itself. But nevertheless, we stick to this language because it seems to describe everything else so well. The entire standard model is built upon this. All these weird facts about nature are very elegantly and minimally addressed by this language. Okay. So with that, let us catch up on where we left off in the last lecture. Okay. Where did we leave off? We started talking about natural units, right? So I said that in the rest of the course I am going to set C equals 1, right, and h bar also equals 1. So why do I do this? Not only does it make life convenient for physicists, for particle physicists in particular, you don't keep seeing C and H all over the place again, but in some sense it is also nature's way of doing things. Okay, for human scales it is fine, we say the speed of light is 3 times 10 power meters per second, because for human scales, for our neural architecture if you want, the meter is an intuitive scale, so you can literally show how big a meter is, right? The second is an intuitive scale. In your mind you can actually tick off seconds fairly accurately and so on, correct? So within these units we have defined convenient units for dealing with human processes, and then we call the speed of light 3 times 10 power 8 in these units, right? And similarly, now I have even forgotten what h bar is actually in SI units, but h bar is something much smaller than 1, right, in SI units. Hence to us it seems like quantum mechanics is in the realm of the small, relativity and general relativity happen to be in the realm of the large, and so on. So these are all very human centric, anthropocentric ways of thinking, but from nature's point of view, right, it does not know what is small and what is large, correct? So from nature's point of view, C is a natural speed limit, correct, in relativity. It is the one speed limit that nature has that we know of in order to satisfy causality and locality and so on, correct? And similarly, Planck's constant is the natural measure of quantum mechanics itself. So from nature's point of view, we can just set these to 1, right? It does not matter what length and time and energy are. We can just set these quantities to 1 and rotate and turn around other measurements and see what is the relation among them, right? So that is what we are going to do. So when we say natural units, we mean natural in both senses of the word. It's both nature's units and in a sense the natural way of doing things for calculations in particle physics. Okay, let us see what has happened now. Since I set C equals 1, what does that mean? I have put the units of length equal to the units of time, correct? So there is no longer meters or seconds. I can even express time in meters if I want. That is what this means to begin with. Agreed? Now one consequence of this is that I can take the Einstein's relativistic equation, right? What has happened here? I have set C to 1, right? It is literally 1, no units for C. That means E, M and P all have the same units. Do you agree? Whatever the units are, we'll see what the units are, but at the least we now know that energy, momentum and mass all have the same units in this system. Agreed? So this is the reason why when I express the mass of a proton, I say GeV, although GeV is in high school we learned this as a unit of energy, right? When we talk about momenta also, sometimes I would have used GeV, right? So GeV is again one unit of convenience, but in general they all have the same dimensionality. Okay. Now I did one more thing. I set h bar equals 1. What is the consequence of that? Where does h bar appear? What is h bar? What quantity would have the units of h bar? Angular momentum. Remember in Bohr's atomic model, angular momentum came in units of in discrete steps of h bar, correct? So that is one way to see it. Another is of course Heisenberg's uncertainty principle, right? delta x delta p was greater than or equal to h bar over 2. Agreed? And since we set this equal to 1, that means the dimensionality or units of length would be the inverse units of momentum, and since we just saw that energy, momentum and mass have the same units, I can do this. Agreed? So let me also write out this. Agreed? So this is something you have to get comfortable with. Time and length I will be expressing as inverse GeV often. Okay, you can, as a little homework problem, you can go find out what your height is in inverse GeV, find out what your age is in inverse GeV, and find out what your weight is in GeV, just to get warmed up with unit conversions. All right? Okay, good. So we will see how this makes life simpler when we deal with particle physics and quantum field theory. So I will wrap up now with one final unit derivation, and then we will see how to translate all this to how we write down Lagrangians, equations of motions and so on. Okay. So one other feature of units is, what is temperature? Isn't it the average kinetic energy? Right? Isn't this how you write temperature? Using the equipartition theorem and so on. Now it turns out in natural units, okay, we also set Kb to 1. In very few contexts people don't do this, but I think that just makes life harder. In most contexts we set the Boltzmann constant also to 1, and what is the consequence of that? That just means even temperatures, instead of expressing them in Kelvin, centigrade, Fahrenheit, whatever, I can express temperature also in units of energy, which is often in particle physics electron volts or giga electron volts and so on. Okay. Incidentally, as a consequence of all this, even from the starting point, what are the units of velocity? The dimensionality of velocity? That just follows from how we started out with, right? The velocity, the speed of light we set to 1. So all velocities, since they are length over time, they have dimensionality of 0 in these natural units. Agreed? Okay, good. So I think it's good, it would be good for you to practice thinking in these units, and we'll see how we apply these to field theory concepts. So I will stop here, and we'll pick up Lagrangians and the cosmological constant problem in the next lecture. Thank you. See you next time.